Okay, so it's 9:30. I guess I'll get started. So I returned the last round of notes and project reports, and I think the project reports were generally good, right? People are happy with I mean, they look good, and I think you got reasonable grades on them. The notes, I think, were a little less. A little more disappointing for people. So let me just. So the first thing on the notes is it's a scale of 4 to 0, right? That does not map to 100 to 0. Think of it as A, B, C, D, right? A, B, C, D, E, right? So a 2 out of 4 is not a 50, it's a C, okay? A 3 is a B, 4 is an A, that kind of thing. So I don't know if that helps at all, but yes.
I guess what's a little bit misleading is that like when that's put in, my courses reports that it's a 50%. It's like you got a 2, 50%.
Oh, okay.
See that?
Yeah. Okay.
It's like dismiss it.
Okay. Okay, so let me look into making that change. Either I'll make the change in the ranging, or I don't know if my courses let you put in A, B, C, Ds. I think it does it. Okay. So I'll fix it. But anyway, just so you know, it's A, B, C, D, not 0 to 100. Okay. So that said, I guess I'm still one thing that surprised me in the notes was that people just a number of people just kind of left out whole sections, right? Like major sections of the chapter in covering them. So I keep trying to think of analogies for what I think you should be doing here, and one is like, okay, so every week I have to get a chapter, right, from a book, and I have to make a talk about it, right? So if you were going to do that, if I handed you this chapter and I said, next week you have to give a lecture on this, what would you do, right? So I don't know. I mean, the first thing that I do is I read through it. And usually I just read through it and I don't take notes. I just read through it to just get a sense of what's in there and what the organization is. And then I look at the section headings, right? Because that's like a key to what the organization and what the important things are, and I write those down, right? Or make slides that are those major headings. And then I go into each of those and I sort of figure out what's important in each of those things, okay? So, I'm not trying to make this a painful thing for you all, but I think it's an important skill to have. So, any feedback to me on what you're, yeah?
I guess it's just a little bit misleading that we need to have comprehensive notes on every single portion of it.
Okay.
It's like I decided to take less notes on stuff that I had already covered in previous classes.
Okay. Well. Okay. Well, so if you look in the syllabus, right, I put rubrics, right, for all the different assignments. So.
You just need to cover all of them.
Yeah. So one of the rubrics says complete, right?
But I mean, complete doesn't mean.
Well, what do you want me to say? Comprehensive? Comprehensive?
That's why we're confused, like, what does complete mean? Like, that you completed. Just knowing that, like, even if you know the stuff, because like when I take notes in the class,
Yeah.
something,
Uh-huh.
That's kind of what
Okay. So I guess that it's not. So I guess maybe in your case, think more about the lecture thing, right? Even though you know it, if you were going to try to teach it to somebody or explain it to somebody, right? Yeah. Okay. Anything else? Any other? Yeah.
So why did the first note go to 0? Are you just not counting?
Oh no. So what happened was when I set up the grades, right? I wasn't thinking, and I just put in, notes A, notes B, notes C, notes D, that kind of thing. And then when I graded notes B, I mistakenly put them in the notes A column, right? And then I put notes C in the notes B column, and someone said, well, no, that's not right. And then I realized my mistake, so I moved them both over, and now there's nothing in the notes A column. and I will take it away as soon as I figure out how to get my courses to do it, okay? So don't worry. All right, other things, other admin-y things, other complaints, compliments? No, okay. All right, so this week is vision. Because we spent a bunch of time at the beginning of last lecture on, what did we talk about? We talked about measurement stuff? No, what did we talk about? Oh, the precision and accuracy. So rather than just having project stuff today, I'm going to be spending a fair amount of time on the rest of this material. So where we were is we were talking about the optical properties of the eye. And I said, that you can think about the eye as an optical system, right? In the front, there's the lens and the cornea and the iris that focus an image on the back of the eyeball in the retina. You can characterize the quality of the image that is produced on the retina in terms of a point spread function, right? So if you have a point of light going in, because of diffraction and aberrations in the lens, you're going to get a distribution of light, and that distribution is called the point spread function. Okay. And what this shows is that the point spread function of the eye changes with different levels of illumination. At high levels of illumination, the pupil is small, and the point spread function is relatively narrow and limited only by diffraction that's produced by the pupil. Okay? At lower light levels, the pupil opens up to allow more light in so that you can see it all. And because of aberrations in the lens, the point spread function gets bigger. Okay? But you can see. Okay? So, okay, yeah. Now you'll never see that again. Okay, so when we talk about the resolution, right, the ability to see detail of the visual system, we're usually talking about we usually use the term acuity, right, your ability to see fine detail. And so if you ever go to the doctor or the clinic or whatever, they'll do an eye test. They often use the Snellen chart here, right, and they ask you to read the letters. And the way they can tell your acuity is because each letter in the Snellen chart, each stroke and space in the letter, has a particular size to it. Okay, and so up at the top, the strokes and the spaces are very big. Down at the bottom, they're very small. And in particular, the 20/20 line, this one here, this is 20/20 vision, right? We talked about 20/20 vision. With 20/20 vision, the strokes and the spaces are separated by 1 minute of visual angle. Remember, we measure the size of features in terms of visual angles. And so 20/20 vision means you can resolve features that are separated by 1 minute of visual angle. Okay? So why is that interesting, aside from just knowing it? Well, the relation here, there's this relationship between the resolution of the visual system, right, the acuity that we measure in a clinical test like the Snellen chart, and the contrast in the image that's on the retina. Okay, so if you think about, here's these two bars, okay, and so now you're looking at these two bars, and on your retina is a distribution of light that's produced by these bars. Okay, actually I see now that it's inverted, so these would be white bars on a black background, okay, because it's bright, right? But you get the idea. So because of the point spread function, right, each one of these bars is going to produce a distribution of light in the retina, and because the bars are close, those distributions are going to overlap. And so what you get on the retina is this pattern of light where there's these two peaks and a little dip in the middle, okay? And as you move the bars closer together, those distributions overlap more and more, and at a certain point, there's no dip, okay? And so there's no way for your visual system to tell whether there's 1 bar or 2 bars there, okay? So what this means is that the resolution of the visual system, your visual acuity that you measure in the clinical test, is a function of contrast sensitivity. So your ability to see, to discriminate the fine detail here, is based on your ability to see the contrast between these points, okay? To see the difference in intensity between those points. All right, everybody with me? So that's why people who study vision are very interested in measuring contrast sensitivity, right? Remember the contrast sensitivity function. So how do we measure contrast sensitivity? Well, one of the ways that people do it is by creating these sine wave gratings, right? So a sine wave grating is a pattern of light, varies sinusoidally, light and dark, right? It has a certain spatial frequency. So this is a relatively low spatial frequency, higher spatial frequency, right? And it has a contrast, which is the difference between the maximum luminance and the minimum luminance divided by the sum of the maximum and the minimum luminance, okay? Anyone remember what this contrast is called? Another name for that contrast? Nope, close. Starts with an M. Nope. It's called Michelson contrast, okay? Anyway. So that's the contrast, is how we measure what's the amplitude of the difference between the light and the dark, okay? And the frequency is measured in cycles per degree of visual angle. So, how many bright and dark bars can you see within a certain visual angle? All right, so people have done experiments over the years to measure the contrast sensitivity of the visual system. And the way they do it is they show somebody some sine wave gratings, right? And they either vary the contrast themselves, or they have people turn a knob and vary the contrast of these gratings until the grating is just visible or just invisible, right? It's at threshold, right? And then you repeat that process for gratings of different spatial frequency. And then what you can plot out is this contrast sensitivity function, which shows the sensitivity to contrast as a function of the spatial frequency of the grating, okay? Now, the thing here is that what you're varying is you're varying the contrast of the grating, okay? And the sensitivity is the reciprocal of that, right? So if you have low contrast in your grating, you have high sensitivity to contrast, okay, and vice versa. So the sensitivity is the reciprocal 1 over the contrast at the threshold, okay? So this is the contrast sensitivity function. You've probably all seen it before, right? It has this particular, at normal, levels of illumination, it has this kind of inverted U shape. It peaks at about 4 cycles per degree, right? Moderate spatial frequencies, and falls off at both higher and lower spatial frequencies, okay? And so one point that's important to connect is that the cutoff frequency, right, of the contrast sensitivity function is the same as your visual acuity, right? This is the finest grating that you can see, right? And that is also what is being measured when you're measuring when you're looking at the Snellen chart, right? Your ability to see the finest detail. Okay? Yeah.
The contrast sensitivity function there, is that for the eye as a whole or for a certain class of photoreceptors?
This is measured psychophysically, so it's for the whole visual system, right?
Is there a difference between, I don't know if you can measure it or not,
Yeah.
but would there be a difference in contrast sensitivity for each of the different rod and cone classes?
Yes. Yes. So you can separately measure the cone system and the rod system. Okay, that's one thing you can do. Psychophysically, just like in a human experiment as opposed to electrophysiology, right? you can also measure, and I'll show this later, the chromatic system and the achromatic system, okay? Measuring the response of the individual receptors, basically what you'd be doing there is, so the receptors themselves are, there's this kind of distribution of different receptors in the retina, right? So the blues in particular, the blue cones, are very sparse. So you would expect them to have low contrast sensitivity, right? And the red and the green system would be higher. But I'm sure that data is out there somewhere. I just don't know off the top of my head. Yeah. But this is for the visual system as a whole, right? You have a person there turning a knob, and that's the curve that's coming out of there, right? So it's not just their eye, it's their whole visual system, their brain and everything, okay? All right, so you've all seen this before, I assume, right? See your own contrast sensitivity function. So this is a pattern that varies in spatial frequency from left to right, right? Varies in contrast from bottom to top, right? And so depending on where you're sitting, you should hopefully be seeing some kind of curve like this, where you can see detail below the curve but not above the curve, okay? All right, so, okay, so you've probably all seen that graph, right? The graph of the contrast sensitivity function. The one that they don't often show you is this one, right? Which is that contrast sensitivity varies as a function of the luminance level, okay? So what this family of curves, these are contrast sensitivity functions that are measured at different average luminance levels, from daylight levels, right, all the way down to low nighttime levels, okay? And so these curves up here are for the daylight, right? And you can see, they have that inverted U shape, right? And the units here are trolins. Don't worry about it. Trolins are essentially measures of retinal illuminance. So they are luminance, candelas per square meter, but modified by the size of the pupil. So, there's less, when the pupil is small, there's less light coming into the retina. And so trolins take that into account. But anyway, the high point is here that under daylight conditions, you have the typical U shape in the contrast sensitivity function. As the average level of illumination drops to nighttime levels, two things happen. One is your overall contrast sensitivity drops, okay? So instead of at daylight levels, your contrast sensitivity is, on the order of 1,000, right? Which means that you can see 1/10 of 1% difference in luminance, right? At moderate levels, it's down to 100, so you can see 1%. And at the very lowest levels of illumination, you need a 10% difference, okay? So overall sensitivity drops, overall contrast sensitivity drops from daytime to nighttime. The other thing that happens is the cutoff frequency goes down, right? So under daylight levels, you can see fine detail, right? At nighttime levels, you don't have very good acuity at all, okay? And so what's going on here? Well, the thing is that you're having a change from daylight levels to nighttime levels. Your visual system is adapting, right, in order to allow you to have vision at all. And so the changes in the curves here are reflecting the effects of visual adaptation. Okay, so this is a diagram, a graph, whatever, that shows a bunch of different things about our vision under different light levels, okay? So this is the top line is the luminance, right, of white paper under different lighting conditions. So the luminance of white paper in sunlight is about 100,000 candelas, okay, per square meter. The luminance of that same piece of paper in starlight is about 1,000th of a candela, right, 10 to the minus 3, okay? So we can see our vision works across this huge range of light intensity, right? 100 million to 1. But it's not equally good at all levels, right? So under daylight conditions, we call it photopic levels, right? We have good visibility, we can see things well, we have color vision, and our acuity is generally good, right? At nighttime, under mesopic or scotopic conditions, our visibility isn't so good, we don't see as well, color vision goes away, and our acuity drops, okay? And so why is that? And how does it work? Well, we talked about this last time, and you guys seem to have a handle on it. So there's all these different mechanisms of adaptation, right? The pupil opens and closes to allow more light into the eye. There's the photopigments in the rods and the cones, and they either get bleached at high light levels or they regenerate at low light levels, and that changes the sensitivity. There's the rod and the cone systems themselves, right? The cone systems generally operate at high light levels, the rods operate at low light levels. And then there's this whole neural network of ganglion cells and bipolar cells and amacrine cells that are acting like an automatic gain control circuit, right? So all those things work together to allow you to see under really widely varying lighting conditions, but they produce these differences in your vision at different light levels, okay? So the first thing that adaptation, or the first impact of adaptation is that there are changes in visibility, okay? So your ability to see contrast at all changes from daytime to nighttime, okay? And so one of the ways that people have measured this is through the threshold versus intensity functions, okay? Have you heard about TVI functions before? No, okay. So people trying to figure out, well, you know, how much contrast do I need at different light levels in order to see differences between things? So they ran a series of experiments where they had a big circle like this, right, of a certain luminance, and then they superimposed on it another circle which was of slightly higher luminance, okay? So this is, the background is L here, luminance L. This is L plus delta L, okay? A little increment of luminance, so slightly brighter. And then they varied the level of the background, right, from very, very low levels here, right, to very high levels, okay? So what you're doing is here's your background, and you're varying it from really low to really high, and you're seeing how much of an increment do I need at every level in order to see a difference, okay? And so if you do that, you can plot the background, you can plot the threshold luminance, that delta L, right, as a function of the background luminance, okay? And so if you look at these curves, there's a bunch of things going on. The first thing is that at very low levels, right, your ability to see those differences is governed by the rod system, okay? And so at really, really low levels, the visual system is struggling just to see, right? And it just, you know, it's photon starved, okay? So nothing really much happens at really, really low levels. And so the threshold is constant. But then, as the background level goes up, the threshold also starts to increase, okay? So as the background becomes brighter and brighter, the amount of light that you need to see a difference between the center and the background also increases, okay? That's what this is saying. And over a large range, it actually stays constant, okay? So the way that we express that is that the delta L, right, the increment, is a constant fraction of the background, okay? That's what this line is saying, okay? And that's known as Weber's law, okay? The other thing that's going on here is that at very low levels, the rods are seeing things, right? And at higher levels, the cones are doing the detection, because at low levels, low light levels, the cones are not as sensitive as the rods, right? But at higher light levels, the rods are not as sensitive as the cones, okay? Everybody with me on that? Okay, so what impact does that have? Well, like I said before, right? In daylight, you can see really well, right? The contrast of things looks really, vibrant. And at nighttime, everything is grayed out and dim, and you just don't see as well, okay? So this is a simulation showing the contrast at a daylight level of illumination in this scene and at a moonlight level of illumination in this scene, okay? So one way you can do this for yourself is you take a Macbeth chart and look at it in here, look at it outside, and look at it in a dark room, right? And the range of grays that you will see is really varied, okay? And that's one of the things that we'll talk about later on when we talk about color appearance, right? Is even though these patches go from white to black in every case, the appearance of those differences between the white and the black is going to be very different depending on whether you're in this room, you're outside, you're in dark, you're under red light, you're under green light, that kind of thing, okay? What time is it? 10, okay. All right, so the other thing that happens with adaptation is that there are changes in your spectral sensitivity and the spectral sensitivity of your visual system, okay? I think at the beginning of this lecture, I showed you that the rods and the cones have different spectral sensitivity curves, right? If you take the spectral sensitivity of the rods is just the response curve of rhodopsin, right, of the photopigment in the rods. The spectral sensitivity of the cone system is the combined response of the short, the red cones, the green cones, and the blue cones, right? The long, medium, and the short wavelength cones, okay? And so what people have done is they've taken these responses and they've combined them and produced what are called the photopic and scotopic luminous efficiency functions, okay? And what these curves show is how effective is light, are lights of different wavelengths at stimulating the visual system, okay? So the dotted curve is the rods, okay? And so rods are not very well stimulated by long wavelength light. They're better stimulated by short wavelength light, and their peak response is about 500 or 510 nanometers, okay? The cone system, on the other hand, is much more sensitive to long wavelength light, not so sensitive to short wavelength light, and peaks at about 550, 560, okay? So the spectral response of the rods and the cone systems are different, right? So you're going to get a difference in the color, or in the spectral response, and the color response because of that. Okay, so the other thing that's going on is, remember I was saying that at nighttime levels, the rods are more sensitive, and at daytime levels, the cones are more sensitive, okay? So at nighttime levels, your spectral sensitivity is going to be dominated by the rod system. At daylight levels, it's going to be dominated by the cone system. And at twilight levels, it's going to be a mixture, okay? And so that's what's going on here. So each one of these panels here, right, shows the luminous efficiency curves for the rod and the cone systems. Okay, so the dashed curve is the luminous efficiency for the rod. The solid curve is the luminous efficiency for the cone, right? And you can see at low light levels, right, nighttime levels, your spectral sensitivity is dominated by the rods, okay? So color, you're seeing color by the rods. You're not really seeing color, but your sensitivity is dominated by the rods. At daytime, it's the opposite, right? So your sensitivity is dominated by the cone system. And in the middle, it's a mix, right? So short wavelengths will be detected by the rod system, and long wavelengths will be detected by the cone system. Okay? So that's kind of weird. And the impact of that is that you get color shifts. You get shifts in the how saturated colors are and how bright colors are, depending on what the level of illumination is. Okay? So here, this is daylight, right? Bright, 1,000 candelas. The white is 1,000 candelas. That's, kind of not outside in the sunlight, but in the hallway. Okay, so that's, if you took the Macbeth chart and put it out there, you would see something like this, right? The colors are nice and saturated. You can see clearly the differences between them and so on. But if you took this Macbeth chart and you took it out, and it's a full moon tonight, try it, right? Take the Macbeth chart, go outside, and look at it under moonlight. The first thing that you're going to see is that you can't see as many colors, right? The colors are not as saturated, right? And in particular, the short wavelength hues, right? So here we have, this is cyan and teal, and I don't know whatever. Those are dominated by the short wavelengths. They're pretty much achromatic, right? Because the rod system is seeing them. The longer wavelengths, you can still see a little bit of color in the red, for example, because the cone system is still seeing the long wavelengths, okay? And there's this interesting phenomenon called the Purkinje shift, okay? So under daylight conditions, we generally think of blues as being darker than reds, okay? But under nighttime conditions, the reds appear darker than the blues, okay? And it's because of this change in the spectral sensitivity of the visual system. All right? So high order bit, your spectral sensitivity of your visual system changes with the level of illumination, and that has an impact on appearance. Okay? So the last thing, or not the last thing, next to the last thing that happens with through adaptation is that your visual acuity changes. Okay, and so I showed that in the contrast sensitivity curves, right? At high luminance levels, your contrast sensitivity is this U shape, and you have good high frequency cutoff. At lower levels, the curve drops, and you have a lower frequency cutoff, and that reflects changes in acuity. You can actually just plot the change in acuity as a function of the average luminance level here. And what this curve shows is that this is the highest resolvable spatial frequency, right, grading. And at high light levels, at daylight levels, it's on the order of 50 cycles per degree. Okay? But as the level of illumination drops from daylight levels to twilight levels to nighttime levels, your acuity also drops. Okay? And under low moonlight or under starlight, really, the best you can see is about 5 cycles per degree, right? Which is like 20/100 vision, right? So it's like having really myopic vision. Okay? So here's a visualization of this, right? So again, daylight levels, you can see fine detail down into the low level of the Snellen chart. Nighttime levels, you can't see any detail at all, okay? And if you go even lower, you see nothing but the outlines, okay? Okay, so the last thing with respect to adaptation that's important is that adaptation doesn't happen instantaneously, okay? It happens over a period of time. You all know this, the classic example is you walk in, you decide to go to a matinee, right, at the movies. And you're outside in the bright sunlight, you walk into the theater, you can't see anything, you bump into the chairs. If you stand there for a while, your eyes adapt, right, and then you can find your way to the seat. And then you're inside, you watch the movie goes off, it gets dark, you stand up, you walk outside, and you're blinded by the light. And then, after a few minutes, you're back to normal again, right? So that's dark adaptation and light adaptation, right? And so these are graphs that show the time course of dark adaptation and light adaptation, right? So one of the things is that they're different in their time constants, right? It takes you much longer to dark adapt than it does for you to light adapt. And that's because of what's going on with the different mechanisms, okay? In dark adaptation, you're regenerating the photopigment, okay, and that takes time. In light adaptation, you're basically just burning it up, and that can be done very quickly, okay? So what this curve shows is this is this is the threshold for seeing contrast, right? Remember that spot or the circle in the spot. This is your threshold for seeing a difference as a function of time in the dark, okay? So you start out and you're in a bright environment, and so your threshold is way up here. And then over time, in the dark, they keep testing you, and your threshold keeps dropping. And then after about 7 minutes or so, it kind of flattens out for a while. And then only after about, after about 5 minutes, it flattens out. And then only again after about 7 minutes does it start to drop again, and it keeps dropping all the way out to 20 minutes. And the reason for that is because in the early part of the adaptation, the cone system is adapting, but the cone system can only adapt so far. And then after further time in the dark, the rod system starts to take over and becomes more sensitive, okay? So the flip side is, you walk out from the theater into the street. What happens is initially your threshold, your sensitivity is very high, so your threshold is really low, okay? And then you walk out into the street and it's like, oh, I'm blinded. And that's what's indicated here, right? So initially you can't see very well at all. You squint, it's painful. But then very quickly over a course of, seconds to minutes, your threshold drops, and actually first it overshoots and then settles out toward the, appropriate level of sensitivity for whatever light conditions you find yourself in. Okay? So that's daylight, dark adaptation, light adaptation. And this, again, is a visualization that shows that, right? So here, you're in this room, the lights are on, okay? So 1400 candelas on the white. You turn the lights off, okay? So this is 25 seconds. You've been in the dark. You can't see anything, still can't see anything. After a minute, 40 seconds, you start to be able to see a little bit. After 3 minutes, you start to see a little bit more, and eventually it'll stabilize, okay? The flip side is light adaptation. Now you're in the dark. You're dark adapted. Somebody flips on the lights. You're blinded. You can't see anything at all, okay? Then over time, your vision starts to return, and then you adapt to the new level, okay? So these pictures here are computer graphics renderings, and I just wanted for a moment to step away from color science and relate what's going on here to research, okay? So I'm a psychologist by training, but I spent my whole career in computer science departments with computer graphics people. And so one of the first problems that I worked on was what's called the tone mapping problem. Everyone know the tone mapping problem? So, okay, the tone mapping problem is this. So out there in the world, right, the range of light that's out there in the world is huge, right? So it's 100 million to 1 intensity range between sunlight and starlight, okay? So you have these huge differences in illumination in the world, okay? In any single scene, right, because of reflections off of shiny surfaces or because of shadows under objects, you can have a really large range of intensities, right? So, and I was just putting on the order of 10,000 to 1 from the highlights to the shadows, okay? But the problem is that our cameras and our displays, whether it's electronic displays or print displays, can generally only capture and reproduce very small ranges, okay, on the order of 100 to 1,000 to 1, okay? And so there's this thing called the tone mapping problem, which is how do you take the world, which is huge, and squish it down so that you can make an image on a screen or on a print that actually looks like what you saw in the world, okay? So that's the tone mapping problem. And so people in computer graphics latched onto this about 10, 15 years ago, and were trying to figure out how to address this problem. And so one of the ways that, one of the things they developed, right, because they're computer graphics people and computer scientists, they developed an algorithm, right? And so there's this thing called the tone mapping operator. And the way it works is, you know, conceptually, you have a person, right, a scene observer, looking at some scene, looking at something in the world, and you want the image, you want an image of that on a display to look like the same thing to a display observer, okay? And so you create this thing that's called a tone mapping operator that maps from the scene values to the display values, and the goal is to produce a visual match so that the scene observer and the display observer think they're looking at the same thing, okay? And so there's two main bits to the tone mapping operator. One is a model of the display device, right? So you need to know what's the luminance range that the display can produce and what's the color gamut that the display can produce, okay? But the more important thing is this thing which is visual models of the scene observer and the display observer, okay? And so if you can build a computational model of the scene observer and the display observer, what you can do is you can say, okay, I'm going to model the visual response of the scene observer to the scene and the visual response of the display observer to the display, and then I'm going to find some way to equate those visual responses so that they think they're looking at the same thing, okay? And so that's what I did. My research was basically coming up with these visual models, and the pictures that I was showing you were based on a model of adaptation that we developed, okay, that simulated those changes in visual appearance that happen at different light levels. So it's a place where, you know, sort of basic vision science and the application came together. And so we did stuff, you know, with this handling wide absolute changes in the level of illumination, right? And I showed you these pictures already. So from daylight to interior to moonlight down to really the limits of vision under starlight. And then the other problem that we wrestled with was high dynamic range, okay? So in a scene like this is the inside of a parking garage. There's a huge contrast range between inside and outside, okay? So this is like 100,000 to 1 between outside and inside. And so a single picture, you know, a single exposure in your camera is not going to be able to capture the entire range. And so everyone know about HDR photography? You can take a series of exposures and stick them together and make a high dynamic range image. And you can capture all the information, but you're still left with the problem of, well, how do I squish it down? How do I map it to a display so it looks like what I see when I'm there? And so what we figured out was we developed algorithms based on, again, on adaptation that allowed us to squish it down intelligently so it looks like what you see when you're standing there, okay? So, all right, so back to basics. So in the visual system, there are rods and cones, right? The cones are the things that mediate color vision. We know that the cones are distributed like this in the retina, right? And that they have broadband spectral sensitivity curves, right? So these are the spectral sensitivity curves, the response curves for the short wavelength system, we'll call it blue, the middle wavelength system, call it green, and the long wavelength system, call it red, okay? And so this particular arrangement of the visual system results in what we call trichromatic, right? Or a 3-channel color vision system, okay? And so there's this term trichromacy, right, which reflects that. And what does trichromacy actually mean? So the concept of trichromacy is that because there are 3 cone systems, right, and because they have broadband spectral response, and because each cone system integrates the response across this broad band, what happens is if I show you, if I stimulate your visual system with with light of a particular spectrum, like that shown here, what is happening in your visual system, conceptually, is that spectrum is being multiplied times the spectral response functions of your different cone systems. And then those responses are being integrated to essentially produce 3 numbers or 3 responses in your visual system. Okay, so your visual system sees this and it turns it into 3 numbers, okay, or 3 signals. Okay, let's not call them numbers, signals. And those are the signals in the short, the medium, and the long wavelength systems. Okay. And if you want to write out the equations for that, that's over here, right? So you have this is P here, P lambda is the energy in the spectrum. S lambda, M lambda, and L lambda are the response functions of the cone systems. And we are multiplying these things together as a function of wavelength and integrating and producing those signals. Okay? So that's what's going on. The impact of that is this concept of metamerism, okay, and metamers. And so here's the idea in metamerism. So same visual system here, right? 2 visual systems, or the same visual system stimulated in 2 places. At the top are 2 different spectra that it's being exposed to. Because of the trichromacy, the signals that are coming are in the visual system coming from these 2 spectra are going to be the same, okay, exactly the same. And so the visual system, to the visual system, it can't tell the difference between this one and this one. And so they look exactly the same to the visual system. And there'll be a visual match, okay? So the concept of metamers is different spectra, different physical spectra that produce the same, visual response, okay, and match. All right? So why is metamerism important? Yeah.
So you can tell that's how the colors are the same on the screen in real life.
Right, exactly. Okay, so the reason that it is relatively easy for us to have all this color technology is because of this property of the visual system. If the visual system worked as like a spectrophotometer, right, you would need displays that could produce the right energy at every wavelength, right, in order to reproduce a color. But because of trichromacy, you don't. You only need 3 primaries or 3 sources that you can combine to produce the appearance of everything else. Okay? So that's exactly right. So the thing about metamerism and color technology is that we can take advantage of it, right? So here's an apple, right? The apple is red. Let's pretend that this is the spectrum that I measure off the apple. I multiply its spectrum times my cone response functions. I get a particular set of responses, okay, in the cone system. If I want to make a picture of that apple, I can have a display, and this is kind of a weird display, right? Let's think of it as red, green, and blue lasers, right? But you can have other functions here. So I can take these three spectral lights, and I vary their energy, and again, when I show this mixed light to the visual system, it's going to see the same red as the apple. Okay? Great. You know, that's the, let's go create color TV. Okay, so this is the foundation of color technology, this idea of metamerism and trichromacy. It works. What else do we need to know? Okay, so what else, why is this not a completely pretty story? How does, yeah. Yep. Yeah, that's good. That's good. I hadn't thought about that, but that's true. So there is what's called observer metamerism, right? So there's the idea that there are individual differences in color vision, and so what matches for me may not match for you. Okay? Yep.
Maybe some systems are better at it than others, so you can have varying colors.
Some display systems, you mean? That's true. That's true. So there's, depending on your choice of primaries there and what their spectral emissions are, you will have larger and smaller color gamuts, right? And so you can reproduce some colors better than others. Yep.
It also matters about surrounding noise, like that happens all the background noise.
Exactly. Thank you. So that's what I was gonna. So look, right? Did you see the slide? Did you look at the slide? No. Okay. No. So, this is a philosophical question, but also a practical one. Like, so you look at an apple, and go, oh, the apple's red. But if you look anywhere on that apple, what is the red of that apple, right? The apple varies in color from every point to every other point, right? So it's very complex. The thing that I was trying to get at was what you referred to is that the color that we see, the red of that apple, is going to vary, one, with respect to what its background is, right? Like you say, you saw it against white or against black or against a wooden table or so on, and also with the differences in the illumination, okay? And so if we really want to understand the appearance of that apple, as opposed to just matching two colors under two abstract patches, then we need to understand the effects of contrast and adaptation. And the person who turned us on to that was Herring, right? Remember the slide from the history talk? And Herring, he was interested in the effects of contrast and adaptation on color perception. He had a big fight with Young and Helmholtz over whether the trichromatic theory was right or whether his theory of opponent color was right. And he took evidence from things like this, right? Simultaneous contrast, where those gray squares there, they have exactly the same spectra, okay? And you can do the same thing with colored patches. So according to the trichromatic theory, those two things should look the same all the time because they're exactly the same response in the cone system. But they don't, right? This one looks darker than that one, and it's because of the effects of contrast, okay? It's that the appearance of this depends upon what it's next to, depends upon what you saw before, depends upon whether you see it as flat or three-dimensional. So there's all these effects of context on what you perceive. And after images is also another place where this comes up, okay? And so Helmholtz developed his opponent process theory of color vision. The idea was that our perception of color is organized with reds and greens and yellows and blues and darks and lights opposed to one another, okay? And so what he said you can have things like you can have a bluish green, you can have a reddish blue, you can have a yellowish red, but you can never have a greenish red. Okay, it just doesn't work. And the reason is that because of the way that the visual system is organized. Okay, and so during his lifetime, he had long battles with Helmholtz over this, and but in the end, it turns out that both of them were right. They were just describing different levels of the visual system. Okay, and so what we now know is that in the retina, right, there are the three cone systems, and they have this trichromatic property, right, the broadband three-channel spectral response, right? But just behind the photoreceptors, all those photoreceptors are interconnected with each other, and they interconnect in these receptive fields, right? And the receptive fields are organized in an opponent way, okay? So there are some receptive fields that are light-dark opponent, right? So this is, remember we talked about on-center and off-center? So at the top, that's an on-center light-dark receptive field, right? That's an off-center light-dark receptive field. And then there are these receptive fields that are color opponent, right? So there are red-green opponent receptive fields and yellow-blue opponent receptive fields. And so if you want to know what the wiring diagram is, at the top you have the long, medium, and short wavelength cone systems. And people have figured out that they're basically wired together in such a way with these various weightings to produce an achromatic system, right? The V lambda that has a broadband light-dark response like this, a yellow-blue system that is produces a negative response to blue and a positive response to yellow, and a red-green system that is positive to red and negative to green. Okay, and you can get these systems by summing up and differencing the cone signals in various ways. Okay, and so the take-home message is that both of these guys were right. It's just describing different levels of coding and processing in the visual system. All right, and so you wind up with a visual system that has achromatic and chromatic channels in it. And it wasn't until the 50s that people actually figured out, well, we know that there are these opponent channels in the visual system, color opponent channels, but what are the response properties of those channels, right? How do they code yellow and blue? What signals do they put out to yellow and blue or red and green? And so what Hurwicz and Jamison did in the 50s was they did what are called hue cancellation experiments, okay? So, and these are illustrated here. So first thing is they showed you a green light, right? A green patch of light. And then they gave you a knob and they said, okay, you can add red light to this. Add red light to this green patch until the patch looks neither red nor green, okay? And what happened is it got to a point where the patch looked yellow, okay? It didn't look red, yellow, it didn't look greenish yellow, it just looked yellow, okay? And if you added more, it started to look orange, okay? And so what they assumed was that when you got this state where it was neither red nor green, then the red and the green signals were balanced against each other, okay? They were equal in the system. And at first glance, you would think, okay, well, if I add red, because we have this opponent thing, if I add red and green, I should get a neutral, right? But the only place where you get a neutral is when the yellow or when the other system is also balanced, okay? So for example, here's the yellow and blue system, right? So you start with yellow, you start adding blue to it. If the red and green system is already balanced, as you add blue to the yellow, you'll get a neutral, right? But if it's unbalanced, you will get either a red or a green, right? So anyway, so it's only when both systems are balanced, the red, green, and the yellow, blue, that you get neutrals, okay? So anyway, from these experiments, what they were able to do is they were able to plot out the response properties of the opponent systems, right, of those receptive fields. And so you get these curves, right? And here's wavelength. This is wavelength, light of particular wavelengths, okay? So at short wavelengths, right, you see purples and so on, purples and blues. And what is purple? Purple is a combination of a red response and a blue response, right? And then as I keep changing the wavelength, what happens in the opponent system is that the blue response declines, and the red response also declines. And I reach a point in the spectrum where I see blue, right? And this is called unique blue, right? And unique blue is where there's a blue response, but there's no red or green response. Okay, so the red-green response is neutral, and you're getting only a blue response. And so that is the purest blue that you will see in the spectrum. Okay, so I keep increasing wavelength here. So I go from the pure blue, where there's no red or green. Now the green system starts responding, and the blue system starts turning off, and I get a point where I'm getting no blue response, no yellow response. I'm only getting a response from the green system, and that's the unique green, okay? And keep going on and so on, and you can get a place where you get a unique yellow, and it's only at the very end of the spectrum that you get a unique red, okay? So the point of this is that our experience of the spectrum, right, and the colors that we see in the spectrum is produced not just by the response of the cones, but by the response of these opponent systems. And so, you know, we see blues down here, we see greens here, yellows, and so on. And there are particular places in the spectrum that are called the unique hues, where we see the purest of each of those hues, okay, each of the primary hues, red, green, yellow, and blue. All right? Okay. All right, so the other interesting thing about the opponent system, right, and the color coding system is that the chromatic channels in the visual system, the red, green, and the yellow, blue channels, have lower spatial resolution than the achromatic channels, okay? And that's shown here. So the BW curve is the contrast sensitivity function for the achromatic channel, and the YB and the RG curves are the contrast sensitivity functions for the red, green, and the yellow, blue, okay? And the important point here is that, so the resolution of the achromatic system is about 30 cycles per degree, and the resolution of the yellow, blue, and the green, red, green is about 10 cycles per degree, okay? And I don't know how well you can see it here, but these are intended to show you that you can see further down here than you can see in these, okay? Where these are pure chromatic differences, and this is an achromatic difference, okay? So this difference in the resolution of the chromatic system and the achromatic system is used a lot in image coding and compression, right? So those people who are in video, you know, they talk about 422, right? Where you're designating different bits to different channels, right? In the, you know, YCC coding or whatever people are doing these days. That's saying use less resolution, use less bit depth in the chromatic channels than in the achromatic channels, okay? And so here's an example that shows this. So here's a picture, color picture, right? I've taken that color picture and I've split it into its achromatic component and its chromatic component, okay? So this is pure color and this is pure, you know, luminance, okay? If I take the luminance channel and I blur it and then add it back to the color, I get something that looks like this. I get a blurry image, okay? If I do the opposite if I take the color channel and blur it and add it back to the luminance channel, I get an image that looks like this, right? And this is pure truth here. This is just added, this is, I took this, added it to this, get this, take this, add it to that, get this. And so what this is saying is the chromatic system is not seeing the blur, right? And so when you put them back together, you get an image that looks good. The achromatic system is seeing the blur, and so the image looks blurry, okay? And so how is this useful? Well, I've blurred this thing, which means it has lower resolution, which means I can compress it more, right? I can use fewer bits to represent it. And so that's a savings in terms of image coding and compression, okay? So it's a place where, again, where knowledge about the visual system is a big advantage in terms of image, image science, right? Okay, in the last few minutes, color blindness. All right, we talked about color blindness. I showed you Dalton here describing his own color blindness. There are 3 different kinds of color blindness we talked about last time that are related to deficiencies in the 3 cone systems, right? So there's deuteranopia and protanopia, which are related to deficiencies in the green cones and the red cones, okay? And so you have red-green confusions. And there's tritanopia, which is a deficiency in the blue cones, and you get yellow-blue confusions. And so here are simulations that show what that image looks like to people with different kinds of color blindness, okay? So color blindness is pretty prevalent, especially in males, right? Something like 8 to 9% of men have some kind of color blindness. Women have much lower prevalence of color blindness, and the reason is because it's an X-linked trait, right? So so squares are dad and circles are mom, right? So if dad is colorblind and mom isn't, you will have potentially a daughter who is a carrier of color blindness. And so if that daughter marries someone who's not colorblind, they could have a daughter who's also a carrier, they could have a daughter who's not a carrier, or they could have a son who's colorblind, right? And so it travels from mom to son. The only way it travels from mom to daughter is if dad is also colorblind, okay? So that's the reason that many more men than women, okay? So in trying to understand color blindness, right, people who are colorblind make these confusions of different colors, right? And so if you look at the patterns of confusion that they make, they fall along what are called the dichromatic confusion lines, okay? So this is a chromaticity diagram. We'll talk about that next week, right? But the high concept again is that this describes the chromaticity, right? The something analogous to the hue and the saturation of a color. And so people who have different kinds of color blindness will confuse colors that fall along these paths through the chromaticity diagram, okay? And so the deuteranopes and the protanopes are actually pretty close to each other because the red cones and the green cones are fairly close spectrally. The tritanope is almost orthogonal to this because the blue cone has a different spectral response, okay? And so understanding that people make confusions along these lines has led to tests for color blindness, right? And so you've all seen the Ishihara test, I'm sure, right? It was developed by Shinobu Ishihara back in 1917. He made these colored plates. There are a bunch of different kinds of plates that he made. The vanishing plates, that's the vanishing plate over there. Only people with normal color vision see the number, okay? There's the hidden digit plate, where only people with abnormal color vision see the number, and you may see a number in there because the colors are not represented completely accurately by these, right? Don't worry, right? I mean, there's no way to actually exactly reproduce what's in the plates, right? And then there are transformation plates where people with normal vision see one thing and people with color blindness see another thing. So this is a 42 here, right? Normals would see typically a 4, and people with color blindness would see a 2, right? And so then there's also diagnostic plates which tell you whether you are a protanope or a deuteranope, okay? So this is a good screening test, but it's not really, it doesn't tell you how colorblind you are, okay? Before I go on, another research connection here is many years ago I was interested in vision testing, right, and vision screening, especially for kids. And so one thing, I wrote a series, because I was in computer graphics, I made some computer games that would test kids' vision, okay? And so the first game we made was the most obvious one. It was called Dalton's Jungle, and these are just screenshots from it. But it was a, it was a PC game, and it had this green field here, which is like foliage, right? And these animals would come out of the jungle at you, and you had to find them as quickly as possible. And if you found them quickly, you got points. If you didn't find them quickly, you lost points. And so as you're playing this game, what's happening is the colors are changing along the dichromatic confusion lines. And so you play the game, and it's measuring your color vision, okay? And at the end, it tells you, how good your color vision is. We also made another game, which was kind of fun, which was called Magnafly, and it was turns out there's visual correlates of dyslexia. So it was a game, you played this game, it measured your motion sensitivity, and it turns out that that's correlated with certain kinds of dyslexia. So you could have a kid who was in kindergarten who hadn't learned to read yet, who played this game, and it would tell the teacher whether they were, predisposed to become dyslexic, so you could have early intervention. So anyway, again, research connection. Okay, last couple minutes. Farnsworth-Munsell test. There's these chips, right, that go around in hue. You arrange the chips in order, and if you misorder them, it tells you, that you're not sensitive to those hue differences. Okay, I'll just keep going, and now I'll show you in the last 2 minutes, few minutes, 3 minutes, what your project is. Okay, so your project is pretty simple this week, right? So test your color discrimination using the online color test challenge, available there. Now, I changed the website that you're going to run it on. So, did you run it already?
Yeah, so good on the first one. I did terrible on the second one. So
Oh, okay. Well, it only takes 5 minutes or something. Okay, so run it there. The reason I did that one is because it has a better scoring system. And so this is important. Read the item below before starting a test may save you from having to run the test twice. I want you to make screen grabs of the important screens, okay, and include them in your report. So one is what your final arrangement of the test chips is, what your score is. So it'll show the circular scoring on the Farnsworth diagram, and where you fall on the distribution of people, okay? So this just shows screenshots. So there's the starting arrangement of the chips. You drag them around and put them in order, and there's my final arrangement. I click the I'm done button, and it tells me where my errors are, okay? And so the hues go around the outside, and how spiky it is tells me the degree of error that I made. And then it gives me this thing that tells me that, nah, don't worry, you're not colorblind. And that's how I compare to everybody else. Okay? So that's the project for this week.